In this lecture, we will determine how to find a basis for the row space of a matrix and discuss the relationship between the row space and the column space of a matrix through the rank of a matrix. So first of all, what does this term mean, rank? So given a matrix A that could be rectangular, we talked about in previous lectures the row and column space of a matrix. Let's focus for a while on the row space of the matrix. The row space is the space spanned by the row vectors of a given matrix, right? It turns out that we can define something called the rank of a matrix A. So the rank of A is nothing other than the number of elements in any basis for the row space of matrix A. So the rank is defined for any rectangular matrix n by n, but in this lecture we will only deal with square matrices, and further on we'll extend to rectangular matrices. It's the same thing. The process we develop to find the rank of a matrix will involve row reductions. But we will go beyond just, getting to form the so-called upper triangular form like we used for the Gaussian elimination process. And we will also zero out as many elements in the upper triangle as we can. We will illustrate with many examples, and it is basically based on the following lemma and theorem. So the lemma says that given two spans formed by vectors x1 down to xm and y1 down to ys, we say that two spans are equal if each xk could be written as a linear combination of the y's and each yk could be written as a linear combination of the x's. Now we can prove this easily by letting x to be a linear combination of the x's, that is c1 x1 down to cm xm. We assume that xk's are a linear combination of the y's and vice versa. Okay, we start from here, then we try to prove that the spans are equal. So since this is correct, then it follows that since x1 is a linear combination of the y's down to xm is a linear combination of the y's, that means that x itself is a linear combination of the y's. Okay, if you can't see that, just write down x1 as a linear combination of the y's and xm as a linear combination of the y's, plug them back here and try to collect common terms in terms of the y's. So you're going to get some constants multiplied by y1 plus some constants multiplied by y2 down to plus some constants multiplied by yn, and thus x is a linear combination of the y's. Likewise, you can let y to be a linear combination of the y's, y1 down to ys, and hence, since the y's is a linear combination of the x's, that means that y is also a linear combination of the x's. And this means that the two spans are equal, because if I pick a vector at random from the span of x1 down to x1, call it x, then I could also write it as a function of the y's, and vice versa. That could only mean that the two spans are equal. Okay? Now next we have an important theorem that says the row space of a matrix is equal to the row space of any row reduced version of the same matrix. So while you grab a matrix, compute its row space, right? Then if you apply the row reduction process multiple times and you grab all those matrices, then guess what? Each and every one of those matrices have the same row space. Okay? Very important to keep in mind. Well, how do you prove this? The proof is fairly short. Suppose that you started by a matrix A, right? And after an exhaustive series of row reduction, you got the matrix B, right? When I say series of row reduction, to be more concrete, I mean a sequence of elementary row operations, right? As we discussed in the previous lecture. Then each row of B is a linear combination of the rows of A. Can you see this? If you take a look at any of those row reducted matrices, if you take a look at, let's say, a row of B, call it BK, right? It is nothing other than a linear combination of the rows of A denoted by AK. Simple as that. Likewise, we have seen in previous lectures that you can go backwards. Means you can undo the row reduction by going backwards. What does that mean? It means that also AK, oh, let me change the index here. N, Cn, and An. Sorry about, let me correct that. What is An? Nth row of A. Likewise, Bk is the kth row of B. Okay? So since we can go backwards then we can say the same thing all the way around. That is, the kth row of A could be written as a linear combination of the rows of B, right? By using this lemma, since xk is a linear combination of the y's and vice versa, so my xk's here are the ak's, and my ys's, if you will, are the bn's, right? Then both are satisfied, which means that the span of the a's is equal to the span of the b's, right? Well, what does that mean? What does it mean that the span of my a's is equal to the span of the b's? First of all, what is the span of a's? It's the row space of matrix A. This guy, by definition, row space of A. Likewise, this guy is the row space of B, and hence the theorem has been proved. Okay? Let's throw in an example right here. So let's say I've got this matrix A, 2 by 2, which is, let's say, 1, 2, and 2, 4. The upper triangular form of A is, let's do this, 1, 2, 2, 4. We only need one operation. What is it? Trinulling out this guy by replacing R2 with R2 minus 2R1. What do you get? 1, 2, and 2 minus 2 times 1 is 0. 4 minus 2 times 2 is also 0. An all 0 row. Call this matrix B, and this matrix is initially denoted by A. It means that, using the theorem above, the row space of A and B is the same, and consists, in this example, of all multiples of the vector 1 and 2, right? Remember, the span, a basis cannot contain the 0 vector. So, from B, you can say that the row space of B is the span of the vector 1, 2. So this vector, it suffices only this vector to represent the row space of B, and thus A by the theorem above. Now, using the definition of the rank, right, up here, it is the number of elements in any basis of the row space of A. Going back down here, how many elements do we have? We have only one row element. Hence, the rank of B, which is also the rank of A because they have the same basis, the same row space, is 1. Okay? Let's see another example. Let's say my matrix was not as such. It was, I don't know, 1, 2, and 3, 4. And we're interested in finding the row space and the rank of A. Let's do row reduction. 1, 2, 3, 4. Try nulling out this guy by replacing R2 by R2 minus 3R1, right? That said, the first row remains the same. The second row becomes 3 minus 3 times 1 is 0. And 4 minus 3 times 2 is minus 2. Okay, well, we got an upper triangular form, but it's still a bit annoying. Why is it annoying? Well, call this matrix B, applying the theorem above, you get a boring row space. Boring. Why do I say boring? Because this base is, okay, let's say the span of this base is 1, 2, and 0 minus 2, right? Well, the span using the theorem above is also equal to the row space of A, and hence the span of its rows 1, 2, and 3, 4, right? Well, something that looks aesthetically better would be to reduce B even further. Could we obtain an even better basis that represents the row space? Well, yes. How? Let's try to do some more smart row operations. And what I mean by smart is that let's try to get, if possible, the identity matrix. Why would that turn out to be useful? Because if we get the identity matrix, then the row space is represented in the standard bases, 1, 0, and 0, 1. Let's try to see if this is possible. So now let's try to null out this guy to be closer to an identity. How do we do that? Well, instead of R1, I can plug in R1 plus R2. That said, row 2 remains the same, and row 1 becomes 0 plus 1 is 1, and minus 2 plus 2 is 0, right? We're closer. This guy is 1, like the identity matrix, but this guy is minus 2. What do? One more operation, that is, instead of row 2, plug in R2 over minus 2. Divide row 2 by minus 2, and you get the identity matrix. Well, we obtained the identity matrix from A via a series of row operations. That means that the row space of B or A is also equal to the span of 1, 0, 0, 1. What does that mean? It means that the row space consists of all linear combinations of the vectors E1, 1, 0, and E2, 0, 1. And so the row space is what? R squared. We saw that the span of E1 and E2 is down to En is Rn, and hence for n equal 2 we can say the following. So what is the rank of A or B or I? It is equal to the rank of I, which is 2. There you go. We needed 2 elements to represent the row space of A or B. Rank of A is 2. Let's see a bigger example. So this time a 3 by 3 matrix, that is 1, 0, 2, 0, 1, 3, right? And 1, 4, and 5. Let's try to find a basis for the row space, or characterize the row space through a basis, and the rank of A. So we're interested in finding the rank of A and a basis of row space of A. Now, of course, someone can come and say, but the basis of a row space is 1, 0, 2, 0, 1, 3, and 1, 4, 5. Just grab the rows of A, throw them in, voila. This is your row space. This is a basis of your row space. True, but we would like a basis in reduced form. And if possible, could we represent the row space of this matrix by the standard 3 by 3 basis, that is E1, E2, E3? Well, let's find out. Hopefully, if you didn't get an all 0 row, means it is possible, right? So let's start. This is 0. Let's try to null out this guy by replacing R3 with R3 minus R1, right? That said, the first 2 rows remain intact, and the last row becomes 1 minus 1, that's a 0, 4 minus 0, that's a 4, and 5 minus 2, that's a 3. Proceed by nulling out 4. How do we do that? Replacing R3 by R3 minus 4R2, right? That said, the first and second rows remain intact, whereas the third row becomes 0, 0, and minus 9, right? Now, notice that the last row here looks like the 3 by 3 identity matrix, except that this guy is a minus 9. Well, how do we force it to be a 1? Easy. All you have to do is replace R3 by R3 over minus 9. That is, you only divide the last row by minus 9, hence the first 2 rows are the same, and the last row becomes a 0, 0, 1, right? Next, let's try to null out this guy, right? How do we do that? Using R3. Well, instead of R2, I can plug in R2 minus 3R3, right? So the first and third rows remain the same, whereas the second row becomes 0, 1, 0. Last but not least, let's null out 2 by replacing R1 by R1 minus 2R3, and hence you can verify that we get the identity matrix. As previously said, the basis of the row space of A is nothing other than the row space of I, that is E1, E2, and E3. Now I know E1, E2, E3 are initially defined as columns. Well, you can put a transpose here to emphasize that those guys are rows. How many elements did it take us to represent the row space of A? 3 elements, hence the rank of matrix A is 3. Simple as that. Let's do a 4x4 example this time. So imagine you have an A that looks like this. So 2, 5, minus 4, and 1. 3, 8, minus 9, and 2. 1, 1, 7, minus 1, and 1, 2, 1, 0. Question is, what is the rank and what is a basis for the row space of A? As we did previously, row operations on A. I'm going to do this one really quickly. The reason is because we did a lot of stuff, a lot of row reduction problems that by this time I expect you to have mastered it. So instead of R2, I'm going to plug in R2 minus 3 over 2 R1. Instead of R3, I'm going to plug in R3 minus half R1. And instead of R4, I'm going to plug in R4 minus half R1. So I'm trying to null all those guys together. What do I obtain? The first row remains unchanged. The second row becomes the following. Third row and last row. Now let's try to null out those two guys. How? Well, instead of R3, you can plug in R3 plus 3R2. And instead of R4, you can plug in R4 plus R2. What do you get? First two rows remain the same. The last two rows become all zeros. Now let's try to get as many zeros as possible, trying to get it closer and closer to identity. We'll start by eliminating 5. How do we do that? Instead of an R1, you can place in R1 minus 10 R2. And you will get the last 3 rows remain the same. And the first row becomes 2, 0, 26, and minus 4. Now, this is the best we can do. Let's try to make this guy a 1. Let's try to force those two to be 1s. How do we do that? So you divide the first row by 2, and the second row you divide by half or multiply by 2, right? And you will see that you obtain 0, 1, minus 6, and 1 in the second row, and 1, 0, 13, and minus 2 in the first row. Clearly, because we have 2 rows that are all zeros, they cannot be part of the basis. We saw this in the previous lecture. A basis cannot have a 0 vector, right? So we pick the non-zero vectors so as they form a basis for the row space of A. So the row space of A consists, a basis for that actually, consists of the 2 rows of the last matrix we obtained, that is 1, 0, 13, minus 2, and 0, 1, minus 6, and 1. Okay, what is the rank? Well, we have 2 elements, hence the rank of A is 2. And if you're still confused that why is he not picking the 0 vectors, what's going on? Well, I would like to shed light on the previous lecture where we introduced a theorem dealing with subspaces of Rn, where one of the statements was that each vector in a basis for S must be non-zero. Does that mean? It means that if you give me a basis, no element of the basis must be all zeros. And that's why we eliminate the 0 rows from the basis. Okay? Because you're right, if we include them, then the rank is no longer what it is, 2. Because actually, if you tell me, oh, but I want to augment the zeros, right? You can go ahead and add 0 infinitely many times. And hence the rank of any matrix would be infinity. That's not precise. We lose the meaningful essence of the rank, which is excluding the 0 vectors. Okay? Now, I don't need to do a formal definition on the following. There's also something really related to the matrix called the nullity of the matrix. Like the rank, there's the nullity. Now, the nullity of the matrix is, you can view it as the complement of the rank, right? Like, what is the number of 0 rows I obtain, right? In this matrix, it's 2. And guess what? For an n by n matrix, which is square, the rank of A plus the nullity of A is equal to the dimension of A when square, okay? Which takes us to the next theorem. If we have a square matrix, n by n, then the rank plus the nullity is equal to n. You can regard the nullity of a matrix as the dimension of its null space. That is, how many linearly independent vectors I could multiply this matrix to get 0. Okay? A very small remark here would be, again, if you've got a square matrix, then terminology. This matrix is said to be full rank. Full rank means you saturated rank-wise. So full rank when what? When rank of A is equal to something, right? Well, what is this something? It couldn't be more than n, right? Because row operations could not augment rows, right? So the rank of A is n. That's maximum. And what can you say about the nullity using the theorem above? In that case, the nullity of A, or the dimension of the null space of A, is 0. There's no vector other than the all 0 vector that could null my A. Okay? Now, some of you guys that are interested in computational linear algebra, which has to deal with programming functions or writing scripts or I don't know what, even softwares or maybe FPGAs, I don't know what, that have to compute or deal with a bunch of large numbers. I don't know, you have a certain matrix, you're computing its rank, I don't know what. And maybe a question would be of interest here. Is this what a computer does to find the rank of a matrix? Well, no. The process of finding the rank of a matrix using row reduction might seem a bit disorganized. In practice, the rank of a matrix is found by computing the so-called SVD. So keep this in mind. SVD stands for singular valued decomposition. Now the SVD, we will discuss SVD in further lectures. It's not the right time, nor is it the right place to introduce the SVD over here. We still didn't talk about determinants. We haven't introduced eigenvalues, eigenvectors, orthogonal matrices, and many, many other concepts to reach the SVD. For now, just keep in mind that the rank, because really this is the definition of the rank. We're starting from the definition. That does not mean that computers abide by this way of finding the rank. But us people, we have to understand what a rank is. And there you go. This is the best way to see it, through elementary row reduction. So in this lecture, we pretty much did a lot of stuff. We introduced the rank of a matrix, which is the dimension of the subspace spanned by a row of that matrix. You might be wondering, why is he only talking about the row space and not the column space? In future lectures, we're going to actually see that the dimension of the column space is equal to that of the row space, and hence equal to the rank of that matrix. This indeed has an important consequence. For example, if A is rectangular, as you see over here, and M is greater than or equal to N, that is, the matrix is tall, right? The opposite of tall is fat when N is greater than M. Well, let's restrict ourselves to this case. Then rank A should be less than the minimum, okay? Likewise, if M is strictly greater than N, likewise, if M is strictly less than N, then rank A has to be here. So it's always less than the minimum of the number of columns and the number of rows. That's how they're linked, okay? Now it follows that if a matrix is not square, rectangular, either its columns or its rows must be linearly dependent if the rank is strictly less than the minimum of number of columns and rows. Now for small square matrices, we can perform row elimination as we did in the example over here, and we're all happy for 2 by 2, 3 by 3. Okay, stuff start to get really annoying when we're at the 4 by 4 matrix, right? Because, you know, it might get really annoying for us human beings, and maybe also for a computer. You might write a script that performs a lot of row reduction operations and get really exhausted. And you know, there's a lot of, you might write a function that never stops. So the question is there a better way of finding the rank of a matrix? We will see in future lectures that there actually is. And finding the rank of an arbitrary matrix is somewhat complex. and relies on the computation of the SVD, and in particular, the singular values of a given matrix. And last but not least, we saw that for a square matrix, we have that the rank of the matrix plus the nullity of the same matrix is equal to n, the dimension, the number of rows or columns of that matrix. Okay? And the nullity, keep in mind that the nullity is the dimension of the null space of that matrix. Therefore, if you want A to be full rank, the nullity of A should be 0. That means the null space of that matrix is empty. Okay?